Dear students, welcome back to our discussion on refrigeration and air conditioning. So, last class we discussed about a small problem to find out the heat absorbed during the working of Carnot refrigeration cycle. That is the heat absorbed during 4 to 1. Then what is the heat getting rejected at 2 to 3. Then we try to estimate what is the net work done during this refrigeration cycle, like that. Then now let us have a new discussion, that is, now let us try to understand what are the effects of operating temperatures on COP. Operating temperatures means there are mainly two temperatures affecting the performance of a Carnot refrigeration cycle. That is, last class we studied that the coefficient of performance, that is COP, of a Carnot refrigeration system is given by T1 by T2 minus T1, where T1 is the here both T1 and T4 are same. T1 is nothing but the lowest temperature maintained inside in a refrigerator cycle. That is, for example, the temperature of the freezer compartment of our household refrigerator. Then T2 is nothing but the higher temperature maintained in a refrigerator cycle. For example, the refrigerator was rejecting heat to the surroundings. So the surroundings temperature can be assumed as T2. Here T2 and T3 are same, and because it is a TS diagram here. So here T2 and T3 we are assuming it as same, that is we are taking it as T2. So if we look at this expression, that is T1 by T2 minus T1. So how we can increase the coefficient of performance, or how we can increase the performance of our refrigerator? It is a simple mathematics, that is increase the numerator and decrease the denominator. So using that mathematical consideration, if T2 is decreasing, COP will increase. Again, if T1 is increasing, that is the numerator will increase, at the same time denominator will decrease. So again this ratio, that is COP, will increase. So what does that mean, or what is the physical meaning of this consideration, that is that we have just discussed? That is, for a minimum power requirement of a refrigerator, that is for a refrigerator to work at a given capacity, for minimum power consumption of that refrigerator, what should be our consideration, or keep the following conditions? That is, one, T2, that is T2 means the higher temperature side or the surroundings temperature should be kept as low as possible. Okay, then T1, that is the lower temperature side or the freezer compartment temperature, should be as high as possible. But we know in a practical situation, for example our household refrigerator, we cannot keep the freezer temperature as high as possible, because we may have to store our ice creams, our fruits, vegetables, cooked food, sometimes meat, fish, etc., etc. They have to be kept at a sufficient low temperature, so that then only our food items will be preserved for some amount of time. So this consideration T1 cannot be kept as high as possible, but mathematically, if T1 is as high as possible, the COP will be increasing. Then the second consideration, that is T2, the higher temperature side or the surroundings temperature, should be kept as low as possible. But we know for making our refrigerator working, or for making the energy consumption of our household refrigerator to a minimum, we cannot always control the surroundings temperature. Normally the atmospheric temperature is controlled by, it is beyond our control. Okay, so these are only mathematical considerations. But as far as possible, if T2 is kept low and if T1 is kept high, the COP will be increasing. So now let us consider some examples of these temperatures effects on the COP. Okay, how these two temperatures are going to affect the COP. So now let us consider a problem, small problem like this. Suppose a domestic refrigerator is producing refrigeration at minus 25 degrees Celsius. That is, it is it is producing a freezer compartment at minus 25 degrees Celsius. Let the heat be rejected to the ambient or the surroundings, which is at 60 degrees Celsius. Suppose the surroundings is at maintained at 60 degrees Celsius. It is beyond our control. It is designed. It is the atmospheric air temperature. Suppose that surroundings is at 60 degrees Celsius. Find the maximum possible COP of this refrigerator. Okay, so we know the expression for the COP, that is T1 by T2 minus T1. So T1 here is the lowest temperature maintained in the refrigerator cycle, which is at minus 25 degrees Celsius. So we can take it T1 by, so COP is nothing but T1 by T2 minus T1. So T1 is nothing but minus 25 plus 273. That is, for any engineering calculations, if nothing else is mentioned, we have to always take the values in SI units. Okay, so we are converting the temperature terms in degree Celsius to Kelvin. Okay, so the SI unit of temperature is Kelvin. So that is minus 25 plus 273 divided by 60 plus 273 minus of 25 plus 273. So it is coming around 2.91. Okay, so anyone with a calculator can easily calculate this value and get this result. But as engineers, or as an engineering student, we should analyze the significance of this result. What is the significance of this result, or what is the quality of this result, or is this result telling us something? Okay, so let us try to again look at this expression in some other point of view. Actually, the COP is given by refrigeration effect divided by work done. So in the last class, I think in the previous session itself, we defined the COP of a refrigerator as the desired output by desired or the amount of expenditure. So the desired output of a refrigerator is nothing but the refrigeration effect produced by it, divided by the magnitude of expenditure is nothing but the net work done by the compressor. So the refrigeration effect divided by work done is given as here we obtained it as 2.91 here. So what does that mean? So if the work done by the compressor, how this compressor is running? By consuming electric power. Okay, so here in our state, KSEB is supplying the electric power. So using the electric power supplied by our KSEB, our compressor will be doing its work. Then suppose that electrical power consumption is 1 watt. If the work done is 1 watt, what does this mean? This refrigerator will be producing 2.91 watts of refrigeration. So you can see for yourself, refrigeration effect divided by work done is 2.91 here. So if the power consumption is 1 watt, in the denominator, the numerator will be 2.91 watts of refrigeration. So now let us continue with this example, or now let us look into another example with almost the same values. Suppose a room air conditioner is producing refrigeration at a temperature of 5 degrees Celsius, which means the lowest it is producing a temperature of 5 degrees Celsius in the area which is meant to be cooled by this air conditioner. The area meant to be cooled in a refrigerator was freezer compartment. In the case of a room air conditioner, that region to be cooled, it can be the inside of a office space, inside of a living room, inside of a any room to which our air conditioner is attached. Okay, so that the lowest temperature produced in this air conditioner working is 5 degrees Celsius. let the heat be rejected to the ambient. Ambient means the surroundings. The surroundings is here again, it is 60 degrees Celsius. Find the maximum possible COP. Find the maximum possible COP. So here again COP is nothing but T1 by T2 minus T1. So here if nothing else is mentioned, we can take the air conditioner also as working on Carnot refrigeration cycle. So here we are assuming the COP as T1 by T2 minus T1. Here T1 is 5 degrees Celsius. In the previous example, it was minus 25 degrees Celsius. So instead of minus 25 degrees Celsius in the previous example, here we are taking it as 5 degrees Celsius. Here again, the T2 is 60 degrees Celsius, which is same as in the previous example also. Okay, so what is the change happening when we are increasing the T1 from minus 25 to 5 degrees Celsius? So let us again calculate the COP value T1 by T2 minus T1. So the calculation will be, calculation will be again coming like this. So the calculated value of COP will be 5.05. Okay, so as mechanical engineers, as engineering students, what is the significance of this result? Okay, so it is not enough that we just leave our answers like that after getting the calculated value. So as engineers, we should try to appreciate the this meaning of this result. So just like the previous example, here we are trying to understand the significance of this result. How, if the work done, if the work done is by the compressor, which is consuming an electric power of 1 watt, the refrigerator will be producing 5.05 watts of refrigeration. So in the previous example, the refrigerator working on Carnot refrigeration cycle was producing only 2.91 watts of refrigeration when the outside temperature was 60 degrees Celsius. But here the outside temperature is again same as 60 degrees Celsius, but it is a air conditioner. The only difference here is the lowest temperature has been increased to 5 degrees Celsius. So by simply changing the lowest temperature in this refrigerator cycle from minus 25 degrees Celsius to 5 degrees Celsius, we were able to increase the performance of the Carnot refrigeration cycle, which is running the air conditioner. Okay, so significantly it is producing more amount of refrigeration. Now, continuing with this similar discussion, consider a situation where a Carnot refrigerator is making ice at 0 degrees Celsius. Okay, that is, suppose this Carnot refrigerator is creating a lowest temperature of 0 degrees Celsius. Okay, and consider another Carnot refrigerator used for air conditioning. Okay, air conditioner or refrigerator both are working on the same cycle. Okay, suppose this Carnot refrigerator is used for air conditioning at 20 degrees Celsius. That is, one refrigerator is working to produce a lowest temperature of 0 degrees Celsius. Another refrigerator is working to produce a lowest temperature of 20 degrees Celsius. In both the cases, the ambient or the surroundings is at 40 degrees Celsius each. So whose COP will be higher? You think for yourself. You think for yourself based on our previous discussions. Now let us focus on another important parameter in our subject, that is Carnot heat pump. Carnot heat pump. So what is meant by heat pump? Carnot heat pump. I think you might have already learned about this Carnot heat pump. It is working in the same as that of our refrigeration cycle, but here the only difference with respect to or compared to a refrigerator is the desired output is different. That is, a Carnot heat pump or a heat pump simply a heat pump is nothing but a device which is similar to our refrigerator, but it will be um, taking away heat from a low temperature source and it will be pumping it to a high temperature sink. For example, in winter, the outside that is during winter season, we want to keep our inside of our room at a higher temperature than the outside temperature. Normally in winter, the outside temperature, that is temperature of air outside our room, will be lower than it will be at a lower temperature, but we need to maintain the inside of our room at a higher temperature. So what we will do, we will fit a Carnot heat pump. We will fit a normal heat pump. What will it do? The heat pump will pump, or it will absorb heat from the outside air, which is already at a lower temperature. Then it will pump that heat towards the inside of our living room. Okay, so here the desired output is how much amount of heat is pumped or rejected into a space. That space can be the inside of our living room, the inside of any space, like that. So here, just like we discussed the coefficient of performance of a refrigerator, we can discuss the performance factor of a heat pump. So we called the performance of a refrigerator as coefficient of performance. Here we will be calling the performance term of a heat pump as performance factor. So how we can define the performance factor of a heat pump? What is the magnitude of desired output divided by what is the magnitude of expenditure? Okay, so what is the desired output in a heat pump? The heat getting rejected to a low to a higher temperature area, which can be the inside of a living room. So the what is the expenditure in running the heat pump? It is the net work done by the heat pump. So we are discussing a Carnot heat pump, in which all the processes are reversible. So the net work done, or the amount of expenditure, will be heat rejected minus heat absorbed. So here it is the TS diagram, temperature versus entropy diagram, for a Carnot heat pump shown over here. So 4 to 1, it is the heat absorbed from the low temperature air, which is outside our room. Then 2 to 3, during the process 2 to 3, the heat is getting rejected to the inside of our living room. So this much amount, the area under 2 to 3, this much amount is the heat getting rejected. So what is the heat rejected during 2 to 3? What is the heat rejected during 2 to 3? It is the temperature of this process times multiplied by the entropy change happening during this process, that is T2. T2 and T3 are same here, so we are taking it as T2. T2 times S2 minus S3. T2 times S2 minus S3. Again, what is the heat absorbed? Heat absorption is happening during 4 to 1 here. So again, temperature times that entropy change, T1 times S1 minus S4. It is the heat absorbed. So by cancelling out the common terms, S2 and S1 are same, S3 and S4 are same. So we can arrive at a simple relation like this: 1 plus T1 by T2 minus T1. But wait, we have already seen this expression somewhere else. T1 by T2 minus T1. What was that? COP of a Carnot refrigerator. So 1 plus COP of refrigerator, that is performance factor of a heat pump, will be COP of a refrigerator plus 1. That is, always the performance factor of a heat pump will be greater than the performance or coefficient of performance of a refrigerator working on the same Carnot cycle. Okay, on the same Carnot cycle. Then now let us discuss another important parameter in our refrigeration. Now let us try to give a unit for this refrigeration process. Okay, how we can define a unit of a refrigeration? That is, we already know what are the units of length. It is meter. What is the unit of time measurement? It is seconds. What is the um, unit of mass, it is kilogram, like that. Okay, so how we can define this unit of refrigeration? Unit of refrigeration, unit of refrigeration is given as tons of refrigeration. Okay, unit of refrigeration is given as tons of refrigeration, or it is represented as TR. Okay, it is represented as TR, tons of refrigeration, or it can also be represented as TON, tons of refrigeration. So what is meant by this 1 ton of refrigeration? So our idea, the idea of refrigeration was already known to our ancestors, for or our ancestors used this idea of refrigeration for so long. So when they initially used this refrigeration idea to produce ice. So in our earlier times, in the early period where our ancestors lived, refrigeration was produced by keeping some amount of ice in a particular region, so that this ice will be taking away heat from that region, and it was producing this necessary cooling effect or refrigeration. So they have assumed, or they have given the unit of refrigeration in terms of ice production. Okay, so how we can define this unit of refrigeration? It is the amount of heat required to be extracted in 24 hours, that is during one day, from 1 ton of water at 0 degree Celsius to produce 1 ton of ice at 0 degree Celsius. So in simple terms, what is the unit of refrigeration? In order to produce 1 ton of ice at 0 degree Celsius from 1 ton of water at 0 degree Celsius, what is the amount of heat required to be extracted in 24 hours? Okay, so we are talking about conversion of water, liquid water, to its solid state at as ice. So here we are talking about a phase transformation. So latent heat comes into picture. So here we are here we have to consider the latent heat of freezing of water, which is nothing but 335 kilojoules per kilogram, which is already found out by our scientists, various scientists. What is meant by this latent heat of freezing water? It is the heat required to be absorbed from 1 kilogram of water in order to convert it into 1 kilogram of ice. 1 kilogram of water to 1 kilogram of ice. What is the heat required to be absorbed from water? That is nothing but, so in order to convert 1 kilogram of water to 1 kilogram of ice, we need to extract 335 kilojoules of heat from water. Okay, so that is the idea. So here, as per the definition of unit of refrigeration, as per the definition cited here, the heat to be absorbed in 24 hours from 1 ton of water at 0 degree Celsius to produce 1 ton of ice at 0 degree Celsius is equal to mass of the ice produced. What is the mass of ice produced? It is 1 ton of ice. Mass of ice produced times latent heat. Okay, so it will be 1000 in brackets. Actually, it is not a proper practice to um, put in between the units also in when we are writing a relation or a mathematical relation. But in order to make it clear, to avoid some confusion, I am putting the units also along with the values. So here 1000 is representing the amount of ice, mass of ice to be produced, into 335 kilojoules per kilogram, that is the latent heat of freezing of water, divided by, that is all these actions are happening in 24 hours. So divided by 24 hours, 24 hour 1 hour is having 60 minutes, so 24 into 60. So 1 minute is having 60 seconds, so again 24 into 60 into 60. So approximately the value is coming around 3.5 kilojoules per second. So 1 TR or 1 ton of refrigeration is nothing but the value is 3.5 kilojoules per second. So thank you. Let us continue later.